Okay, it's 4 o'clock, so we can continue the evening session of our last but not least day of our conference, MIPT Quant 2020. And the first talk of this session will be delivered by Professor Boris Fine, who's a professor at MIPT, and he's famous for his work, theoretical studies of the complex behavior of many particle quantum systems. And today he will present some very exciting results on hybrid quantum classical methods for simulating complex high temperature dynamics of nuclear spins in solids. So Professor Fine, I'll give you the floor. You have a half of an hour.
Okay, please. Well, thank you very much for this very nice introduction. Yes, and I also would like to thank Mikhail and the organizers for taking care of this conference and for inviting me to present. The subject of my talk is, as you see on the screen, hybrid quantum classical method for simulating high temperature dynamics of nuclear spins in solids. And indeed, I moved to Moscow Institute of Physics and Technology, which I'm happy to represent. And this is the brand new laboratory for the physics of complex quantum system that now exists at MIPT and which I had. The subject of this talk is in many respects about classical versus quantum description of spin dynamics. And let me be specific to talk in the context of nuclear spins in solids. You can think of a nuclear spin classically, and then it is a charged particle which has a classical magnetic moment represented by an arrow, or you can think about this quantum mechanically. If it is a spin 1/2, then it has two states separated by the energy gap, which gives you the Larmor frequency. But both pictures are intrinsically connected at the level of quantum mechanical averages and at the level of Bloch sphere. And this connection is something that people never get tired to explore, and this is also what this talk is about. Let me now briefly introduce you to the nuclear magnetic resonance problem of free induction decay. The free induction decay is formulated as follows. Imagine you have a system of nuclear spins, weakly polarized, as shown on the screen, for example, in the x direction, and then you let them interact, and the polarization decays because of the interaction between them, which you see on the screen, which does not conserve the x component of this polarization. This process is called T2 relaxation in the slang of NMR. The interaction often comes from magnetic dipolar coupling, and it is truncated magnetic dipole interaction, which means that it is the full interaction averaged over the fast Larmor precession. This is an extremely well-posed theoretical problem known since the 40s, since the discovery of the NMR, and it is also very accurately measurable quantity NMR for induction decay, and therefore it is the testing bed for the methods of first principles calculation of nuclear spin dynamics. Nuclei are typically at high temperatures because all the energy scales are very small because of the small nuclear gyromagnetic ratio, and therefore the experimentally measured quantity is simply proportional to the infinite temperature correlation function of the total magnetization, total x component of magnetization, which is quantum mechanically expressed as shown on the screen. Now, the same problem can also be treated classically, and then in that case, one needs to compute one chooses the initial conditions fully randomly, computes classical trajectories of every spin, and then average over them. And then quantum mechanically or classically, the result looks like shown on the screen. So this is an experimental measurement of NMR free induction decay in the standard testing material, which is called calcium fluoride. There are these three numbers indicated on the top. This is the direction of magnetic field, because dependent on this direction, the Hamiltonian is differently averaged. So these are like three different theoretical problems. The problem is has very long history, and as you see from the list, famous people, including 3 Nobel Prize winners, have attempted this. The relevant contributions to this talk is about the purely classical simulations which were tried since the 70s, and then also the ideas on how to treat the lattice in terms of the central cell and the environment, which goes back to the Russian authors Lundin, Provotorov, and Shakhmuratov. And then since mid-90s, there are many efforts to do direct quantum simulations using complete diagonalization and also quantum typicality. So let me, just to give you an idea how hard the story is, let me just present what a straightforward approach does. The straightforward approach is called the moment expansion. So you just expand the quantity of interest in the power series and compute the coefficients of this power series, which are called moments, directly doing computing quantum mechanical commutators. So in this case, the second moment looks like something shown on the screen. You don't need to follow the details here, just to look at the scope of what you get. You get it very quickly. The fourth moment requires much more work, and at the end of the day gives you a formula with some compressed notations, which still looks reasonable. Now, the sixth moment looks like what you see now, so that's already unreasonable and was computed with the help of a computer program. And now the eighth moment looks like this, right? And still it's not enough to accurately reproduce the free induction decay, so one is looking for less straightforward methods to calculate. And then one such method is classical simulations. So here you look at the same Hamiltonian as the Hamiltonian for classical variables represented by classical spin vectors. In this case, the equations of motion look like Larmor precession. In the magnetic, so each spin precesses in a local field, which is created by the, say, by the nearest neighbors, if you have nearest neighbor interaction. And then in the course of the evolution, both the spin changes their orientation and also local field changes. And this is what you need to compute. This is the idea was there for a long time, but it was not until this work that the full potential of this calculation became clear, because it still requires some significant computational effort. So that was done with my former PhD student Tariq El Said, who is now assistant professor at the American University in Cairo. And so here on the screen, you see free induction decay. The red line is the experiment. Also in calcium fluoride, the red line is the experiment. The blue line is the theory. And you see that simply classical calculation gives you either excellent or very good agreement in this particular case. Now, the situation gets a bit worse when you start going to lattices with small coordination number. So here is an example of two-dimensional lattices with nearest neighbor interaction. So you have 4 nearest neighbors, and here the discrepancy between the classical calculation and the experiment becomes more visible. And when you go to spin chains, then spin 1/2 chains, you can obtain some results by direct calculation or diagonalization. And here you see that black lines, the classical results, black dots, they significantly deviate from the direct calculation. So the quality of the classical approximation drastically reduces as one reduces the number of interacting neighbors. And so here we introduced some quantity which quantifies for the case when you don't have, theoretical models, but for example, magnetic dipole interaction. It gives you an effective number of interacting neighbors. And so here there is a rigorous analytical result by Lundin and Zobov that in the limit of this number of interacting neighbors going to infinity, the classical simulations are supposed to be rigorously accurate in the context of quantum problems. But then there is this practical result that comes from our paper that already when you have lattices of spins 1/2 and more than 4 nearest neighbors, that's already good. And if you have quantum spin more than 1, then already 2 nearest neighbors give you a reasonable result. However, lattices with less than 4 nearest neighbors are not so uncommon. There are solids with quasi-one-dimensional spin 1/2 chains. In the context of NMR, the prominent example is fluorapatite. There is also an object, diamond, simply diamond lattice, which can be enriched by nuclear isotopes carbon-13, which have spin 1/2. And in that case, the Hamiltonian depends on the orientation of magnetic field, and there is a particular orientation when the free induction decay is just dominated with the coupling with 1 nearest neighbor, and so it's also the question of practical interest how to deal with this. And on purely theoretical ground, you simply want to control everything, right? So you simply want to be in position that if you are given a lattice, you present the free induction decay or echo, and you are responsible for your predictions, and you just responsibly tell to the experimentalist what the result of his measurements should be. Now, another relevant piece of knowledge is which was also established previously, is that spin lattices at high temperatures, both classical and quantum, have generic long-time behavior, which is asymptotic tails, which are shown here on the screen. So they decay exponentially, maybe with some oscillations, maybe without oscillations. But the important thing is that the constants of this decay or the oscillations, they are not slow constants. So it's not the case of damped oscillator. And but rather it was conjectured, and this conjecture was sort of supported by all kinds of arguments in this paper, that this sort of behavior is a manifestation of chaos in the systems, right? So this prediction, the existence of these tails was tested numerically for classical spin lattices, and also experimentally it was measured in the NMR group in Leipzig with huge precision. You can see here that this is a logarithmic scale. So the free induction decay going down 5 orders of magnitude and excellently following this behavior. So this is interesting problem on its own, how, for example, to compute this long-time decay constants. But in the context of, say, more practical calculation, well, all you need to know is that just your signal classically or quantum mechanically eventually decays exponentially. How exactly it decays may be not so important for you practically. The fact is that it decays, right? And so what is necessary to make an accurate prediction is to move closely enough to the time range when you start getting the exponential decay. Now, another ingredient of this work that I'm going to present is related to the simulations of pure quantum states to the subject of quantum typicality, right? So this was obtained also in my joint work with Tariq El Said. And so what we have shown there is that if you deal with pure many-body quantum state, so suppose you have a lattice and you just arbitrarily pick superposition in Hilbert space and let it evolve as a function of time, and you track the quantum mechanical expectation value of some observable, for example, total magnetization, then in terms of this quantity, there is an analog of the Ansager regression relation, which is in turn the high temperature limit of the fluctuation dissipation theorem, that the relaxation of the quantity of interest, which is to say the free induction decay, is proportional to the autocorrelation function, which you can extract from just simulating the time series, or measuring, not actually simulating the time series of the quantum mechanical expectation value. And this we have also tested numerically. It works. It was proven basically as a theorem. Now there is a catch here, and the catch is in this prefactor. So one thing that you should appreciate is that when you do not measure the system but take an arbitrary superposition of quantum states, it's like you have in parallel exponentially many quantum mechanical evolutions, and you have averaging over this exponentially many evolutions, and so your expectation value, which you plot here, is exponentially suppressed, and this exponential suppression is compensated here by factor n, which is the dimensionality of the Hilbert space. And with this comes a subtle point which I want to represent now, and it is the following. Suppose you have a system of n classical spins, and you look at an equilibrium magnetization noise, right? So in that case, the root mean squared value of this noise, the amplitude, is going to be basically proportional to the square root of the number of spins in the system. Now I make interesting claim which you can think about, and it is the following: that if the equilibrium noise is monitored in quantum system of spins 1/2, so you actually try to monitor it, but the system is very large. So by monitoring the total magnetization, you still do not perturb significantly the individual evolutions of every spin. Then your noise will be also proportional to the square root of n, the same as classically. But now, if you don't measure your system, but rather simply do numerical calculation and compute the quantum mechanical evolution, then your equilibrium noise, according to this result, has exactly the same autocorrelation function, with only the difference is that the typical amplitude is going to be exponentially smaller. And so it is this exponential suppression of this noise that we need to deal with in our work. And with that, I move to basically the new subject that I wanted to present in this talk, and this is the hybrid method, which mixes the quantum and the classical system. It was done together with Grigory Starkov, for whom it was the main part of his PhD thesis, and who is now a postdoc at the University of Bochum in Germany. So the idea in principle seems to be rather natural. Why not to choose a cell which in the middle you simulate quantum mechanically, and on the sides the rest of the spins you simulate classically? It turns out the problem here is precisely this exponential suppression of the quantum mechanical expectation value, because in this case you can rather easily simulate the influence of classical subsystem onto the quantum one, but to have a back action, how quantum subsystem acts onto the classical one, you need to do something, because otherwise your quantum mechanical expectation values are going to be exponentially small, and there will be no effect on the classical part. And this would contradict to the physics, to the actual physics of the system. So let me just to justify it further, let me just give you this quick comparison of quantum and classical dynamics, sort of back to back. So quantum mechanically, so for the central part, you simulate quantum mechanical spin operators. Classically, you simulate classical spin vectors, and in this case, the length of this vector is the same as the length of the corresponding quantum spin vector. The Hamiltonians look exactly the same. Now, when you do quantum simulations, your dynamics, you commute your variable of interest with the Hamiltonian, and you use in doing this you use standard spin commutation relations, and classically you use Poisson brackets, right? And the algebra of classical Poisson brackets and quantum spin commutators is basically nearly the same. With this, you get the equations of motion for quantum spin operator, Heisenberg equations of motion, or classical Larmor-like equations, which are, again, basically identical. And the difference is that here the local field is a quantum operator, whereas classically it is just a classical vector. So far, so good. Now comes to the correlation function. So classically, you just say, you simulate the equilibrium fluctuations of the total magnetization, and then you extract the correlation function from this time series of these simulations. Quantum mechanically, likewise, you can simulate the time series of quantum mechanical expectation value and extract from this time series the correlation function, but the normalization is going to be different. So in that case, you would need to make it exponentially larger. And so now the simple proposition that we made is, when it comes to separate evolution of quantum and classical parts, everything looks okay. Now we are coming to the interaction between the classical and the quantum part, and then now this is how hybrid lattice is defined, right? So here this is HQ is the quantum part with quantum internal quantum interaction and the coupling of classical field acting on quantum spin operator. And this is the classical part, this is the classical Hamiltonian, and this is also some field which is produced by the quantum part which acts on the classical spin operator. And so the classical local field is defined exactly the same way as the classical, this field is defined exactly the same way as in the classical simulations, but quantum field that acts on the classical part is multiplied by the square root of n, where n is the dimensionality of the Hilbert space of this central cell. The quantity of interest is also defined analogously. So if we want to look at the full magnetization, we add the contribution from the classical part and also add the expectation value from the quantum part, but we multiply it by the square root of n. And so this becomes our quantity of interest. There is also an auxiliary quantity, which is something like this, but defined in the center of our quantum cluster as far from the boundaries as possible to minimize theoretical errors. And then with this is our quantity of interest. And so this is ad hoc assumption, this prescription that you multiply it by square root of n, but at least we can show that it works in purely classical and in purely quantum limit, and also it conserves dynamically conserved quantity. So this consistent multiplication by square root of n here and in the local field helps you to conserve the quantity of, for example, total Z polarization if total Z polarization is conserved. And then the rest is a matter of trial and error. So basically you test it, and it turns out that this way there is an internal, very important, internal consistency criterion when we can say that the calculation converged without looking at the experiment or at the exact result. And but in any case, of course, it is important to test the method, and these are, now I'm presenting the results of this test. So so these are the results for one-dimensional lattices of spins 1/2. So the left column is the hybrid simulations, the right column is purely classical simulation, so that you can see how hybrid simulation improves over classical one. This is compared with really numerically exact calculation for the same chain in the thermodynamic limit. So this yellow reference curve, right? And so you see that say in this case hybrid simulations significantly improve over the classical ones. this is another example where the classical simulation just misses some qualitative aspect, but the quantum doesn't. Now, this is what you see at the bottom is basically the worst case scenario, right? So in that case, the reference curve looks like this. The classical simulation misses it altogether, but the quantum simulation, of course, qualitatively looks similar, but still here there is significant discrepancy. Now, important is that this discrepancy you see internally in the hybrid method without comparing with the reference curve, because you can do it with different size of the quantum core for this hybrid method, and you will see the difference, and you will know that once these two curves deviate from each other, this means that the predictions of the method are no longer reliable, and this is indeed what you see just by the direct test. So it is very important that the method actually became predictive, and it is first of a kind in this sense. Now, for two-dimensional lattices, I mean, that's just, you know, to just test just in case, of course. Hybrid method here works very well, but here the classical method would work also satisfactorily as we knew from the early work. The same, we have also done this test for this free induction decay in calcium fluoride, and so in two cases the agreement was perfect. You just don't see the difference between the lines. But say in this case, when the effective number of nearest neighbors is marginal, so to say, the hybrid method arguably gives better agreement with the experiment. Now, but the crucial test, you know, the reason we wanted to do it was to test. So the worst case for all this semi-classical or quasi-classical calculations is the case of low number of interacting neighbors, and so here we applied it for sample with enriched silicon. So silicon, silicon has a diamond lattice, right? So it is a diamond lattice of spins 1/2, and magnetic field is oriented along the main diagonal. So you know that the diamond lattice, it is two face-centered cubic lattices which are shifted along the main diagonal of the cube, right? And the magnetic field is oriented also along the main diagonal of the cube. And then the truncation of magnetic dipole interaction is such that each spin has one strong nearest neighbor, and the coupling with other nearest neighbors is accidentally very small, almost zero. So it's a relatively difficult case for theory. And so here you see the experiment. On the central panel, you see the free induction decay, basically the Fourier transform of the spectral function. It is this orange line. And so here the theory gives fairly good agreement with the experiment, whereas classical calculation, this dashed line, would be noticeably different. And if you do Fourier transform, you get the absorption line shape. And here you see again that theory gives a good agreement with experiment. Here, by the way, the experiment presumably has uncertainties of its own. So we still don't know. Maybe the agreement with the theory is even better. For comparison, there are calculations of other people and other groups for the same material. And I mean, if you say look at the central curves, I would say that we are getting closer. And also in our case, we do have this internal quality predictive criterion, which will tell us that our prediction should be reliable here. So with this, let me conclude that I presented the hybrid method of quantum classical simulations. It is mostly very accurate method of predicting NMR for induction decay from first principles. The method has been extensively tested, more extensively than any other method, and it is the only method that comes with an efficient estimate of the predictive uncertainty, which makes it really the method for first principles prediction, probably the first of a kind. And the outlook is that now this machinery, we plan to extend it, say, beyond NMR and beyond free induction decay. So the problems of our next interest are decoherence problems of electronic spins of NV centers in diamond, and also just spin echo calculations in general. Thank you for your attention.
Yeah, thank you very much, Professor Fine, for a nice talk. So now it's time for questions. So I believe that we have time for 1 or 2 quick questions. Yeah, Vladislav, I see your hand.
Hello, can you hear me?
Yes.
Yes.
Boris, first of all, thank you for the very nice talk. I have a more or less naive question. I'm curious how your approach when you define this quantum described part and classical, how close is it to a mean field theory? Because I would assume that how different it is from describing the rest with a mean magnetic magnetization vector.
Well, the short answer is that this is the story of high temperature dynamics. So any mean quantity like mean field is simply 0 in this case. So the mean field from the classical part on the quantum part is 0 and vice versa, right? So you really need to define something related to fluctuations.
All right. So you assume that the temperature is ambient.
It is right. So for the interaction between nuclear spins, the temperature becomes of the order of the interaction something on the scale of microkelvin. So even the experiments at millikelvin or 1 Kelvin, you can still accurately treat them in the high temperature approximation.
Okay, interesting. Thank you.
You're welcome.
Yeah, thank you. Okay, I believe if you don't have any questions, so there is a time for the next speaker. Thank you again, Professor Fine. It was a really nice talk. So the next speaker is Vladislav Bushmakin from Stuttgart University and Stuttgart Research Center of Photonic Engineering, who also presents Max Planck Institute of Solid State Research. And I have known Vladislav for a long time since we were students at MIPT. And I had a pleasure to graduate from the Department of General and Applied Physics at the same year as Vladislav. And today he'll present some very intriguing results on experimental realization of a single photon source. So please, Vladislav, you can start. We look forward
to
your
for
talk.
the very kind introduction, Misha. First of all, I have to share my screen. Sometimes it's problematic on Mac and Zoom. Do you see my presentation or the...
Yeah, we can see.
Okay,
yes,
very good. I'm a little bit lost, so to say. Okay, yeah. Yes. Do you see my presentation now?
Yes.
Okay, awesome. So my name is Vladislav Bushmakin, yes, and as Misha said, and I work in the large group of your graph group, but I work not on the huge part which this institute is mostly devoted to. It's mostly devoted to solid state systems like NV centers or silicon carbide. I work on a little spin-off working with organic molecules, and today I will be presenting. I'll present you sort of a short experiment, actually, a pretty simple experiment, which I believe can lead to quite interesting consequences. So I recently was scrolling my feed on Twitter, and I've stumbled upon a very interesting news about a new company which has raised a lot of money from investors on building a first useful quantum computer. And this company was founded by Jeremy O'Brien, a former Bristol professor, who claimed in one of his interviews to Forbes that they can achieve 1 million qubits within 5 years. And to be honest, I doubt that this will be possible. But anyway, I'm very optimistic about this approach to quantum computing and quantum technologies in general. So to give you a brief overview, just a look at what they are trying to achieve, let's have a look at one of the papers featuring Jeremy O'Brien, where they try to generate a multidimensional quantum entanglement state with integrated optics. And what they are bringing into science and technology, they are trying to make large-scale quantum linear optics schemes. And nowadays, due to very rapid development in photonic computing, not quantum, but purely photonic computing, and the very rapid development in the developing of these photonic chips on a silicon wafers. So, for example, in this experiment, they managed to generate a multidimensional entangled state using such a chip with a bunch of spontaneous photon pair sources, and by routing these photons generated in the spontaneous photon pair sources, they can using the so-called Hongo-Mandel interference, where indistinguishable photons fall onto a beam splitter at the same time, they interfere, and it is a possible resource for generating a large-scale entanglement. And yes, this approach is very, very intriguing. However, it has one interesting it has one disadvantage. It uses spontaneous sources, which are by their nature are spontaneous. And in order to understand why this is disadvantageous, let's have a look at what is Hongo-Mandel interference is and how can we generate entanglement with photons. So first of all, Hongo-Mandel interference is the very interesting effect when two single photons are coming at a beam splitter at the same time, and if they are indistinguishable, the amplitudes can destructively interfere of these photons, and the output state of such
Sorry, can I interrupt, because there is also on the chat, are you moving to the next slide, or are you talking about the first slide now?
Oh, I moved quite a bit.
Because we can see only the first slide.
Thank you, sorry. Okay. That's how usually it goes with Mac and Zoom. Okay, can you see not the first slide?
Yeah, now it's good.
All right. Okay, so yes, Hongo-Mandel interference. So the photons, a photon can interfere with a photon if they come at a beam splitter at the same time and generate entanglement. But this process would occur if these photons are indeed the same. So they are the same spectrally, they're coming at the same time at the beam splitter, and they are in the same spatial mode. So they have to be indistinguishable. And thus, a single photon source has to satisfy all these conditions. And let's look at the first condition, that they have to come at the same time at the beam splitter. And this is sort of a problem with spontaneous sources, that the photons intrinsically don't come at the beam splitter at the same time. And the way to overcome it is to use deterministic sources like single emitters, which are supposed to be at two-level systems, but it's often quite hard to get a two-level system, especially in a solid state, but it's most convenient to work in a solid state. So we are concentrated on one of the sources and one of the ways to generate photons. These are organic molecules in glass-like host matrices. And let's have a brief look at how how is it possible to generate almost perfect single photons with a molecule in a glass-like matrix. So the molecules we are using are DBAT molecules, the organic molecule which at 1 Kelvin, and it's questionable, maybe a little bit higher, 1-2 kelvins, it can reach Fourier limited performance, because the host matrix which is formed at these low temperatures and enables this.
I'm sorry to interfere, but are you moving with your presentation? We are still on.
Yes. All right.
So now we're stuck on 4th slide.
Okay.
So this was the molecule you were talking
sorry.
about. Okay.
Yes, I'm so sorry. This is.
Yeah. Vladislav, maybe let's make a little check. So can you move forward to 7th?
Yes, let's
slide?
do it. Okay. Can you see my slides?
No, we start on
Okay.
the 6th one.
Maybe you should go into the mode which just shares your entire screen, so that we see whatever you see yourself on the screen. And then once you progress, we will see also the same.
Maybe like, okay, let's try this. Yeah, because when I click on show the presentation on Mac, it sort of splits the screens automatically. Can you see it now?
Yes.
Yeah, now it works fine.
Now it's perfect. Yes.
Awesome. Okay. All right. So yes, we are using organic molecules, which can in principle be and are actually a very nice single photon source. They are spectrally stable in comparison to the most solid state single photon sources. They are a narrow band, which is very beneficial for using the photons generated by a molecule as an interface these photons with, for example, atomic vapors, rubidium vapors or sodium vapors, which was shown by, for example, in the work of Peter Styushev in 2014, where they used a sodium cell as a Faraday filter for these photons, which led to a very, very stable and almost perfect single photons performance. And these molecules are also tunable with Stark effect, and these are all conditions which are very beneficial for using it for quantum technologies. And in comparison to other solid-state single photon emitters, according to the paper of Christoph Becher, the molecules are the best at remote Hongo-Mandel interference, which is the most useful experiment for solid-state emitters, because what we would want to do, we would want to take several remote emitters and generate photons which are indistinguishable. And the molecule we're using is quite bright. So today we could detect up to 2 million counts at saturation, but actually it can be much brighter because, for example, as in the work of the group, from the group of Vahid Chandogdar, from Max Planck of light sciences, they showed that it's possible to collect up to 96% into free space of the whole emission of a molecule. But in order for this emission to be useful, it has to be emitted into one spatial mode. And in order to do so, it would be beneficial to try to couple a molecule to a single mode fiber. And then automatically we would satisfy this condition. So a molecule can in principle satisfy all the conditions, but we need to couple it to the simplest waveguide available, just couple it to optical fiber. So this would be the first step for us to show that it's possible to get a photon into a single mode with the organic molecule. And in order to get into this field, let me introduce you to give you a brief overlook over the recent works. So this is a work from the group of Stefan Ratzenstein from Berlin, together with Harald Giesen, where they 3D printed a special ferrule, where they placed in the center of the ferrule, they placed a quantum dot, and deterministically they could put the fiber into this ferrule and make an integrated, a sort of quasi-integrated single photon source. So this is not yet published, but it's very interesting to see where it will develop. But the earlier approach of this group was just the simplest approach. They took a quantum dot with a micro lens, and they just glued a fiber onto it, and they could see it. So they got single photons, but it was reasonably dim source, but anyway, they could see single photons. So why shouldn't we try the same? Because our molecules they exist at room temperature in a liquid. So the molecules are usually dissolved in tetradecaying. So what we could try just take a fiber and dip it into this liquid and try to see some molecules. We believed that we will see something because our matrix, the matrix the molecules are in, has a quite broad inhomogeneous broadening due to the fact that the matrix is an amorphous lattice, and all the molecules are oriented different and experience different nano-environments, so to say. And that's why it's possible to spectrally select single molecules. And in order to estimate what could we expect from this simplistic approach, let's just have a look at what governs the coupling to the fiber. So it's basically the Na of the fiber, the opening angle. It's just the angle at which the light would propagate inside the fiber. Just simply calculating in Mathematica and looking at how much would we collect if we assume the dipole emission of a molecule, we could see that the coupling efficiency is not very impressive, but anyway, we would see something if it's 6%. So if we can get a fiber with 0.4 Na and collect 6%, so in principle from 2 million counts, we would get with extra losses, maybe 100K, we could see. And in order to start this experiment, we have bought an optical fiber UNA7. This was the only achievable, just simply available on the market, a fiber with 0.4 Na, 0.41. But unfortunately, this fiber was not a single mode for our wavelength, because our wavelength is 590, 589 nanometers. And this one is the cutoff is far from our wavelength. So this is not a single mode at all. And in order before the experiment, we tested the fluorescence of the fiber. We shoved in some 589 laser and looked with a spectrometer to see if there is some extra fluorescence coming from the fiber. And indeed, as we collect only red-shifted photons from the molecule, and we see that the Raman scattering in the fiber covers almost all the emission of the molecule. But if we introduce a long-pass filter and a short-pass filter, as is depicted on the right picture, one can see that in principle we can collect 30% of the whole emission with a high background, but at least we would see the molecule, which would be already a thing. So we set up our experiment. The setup is quite simple. We have just the dichroic and the two APDs for the Hanbury, Brown, and Twist experiment. And the molecules were put inside the glass capillary with the solution, and the optical fiber was just shoved into this capillary, and this went into the cryostat. But nowadays, I've designed a tube, and this tube just with the fiber goes directly into the dewar, such that we can do experiments for days and whenever we have helium. And once we set it up the experiment, we scanned the laser, and surprisingly, we have seen the molecules. And this was a very pleasant moment for us. And we indeed could select and see separate molecules on the fiber tip. And so we performed the Hanbury-Brown twist experiment and look at the G2 function to see how single are the photons we are generating. And we could see that the G2 of 0 can go lower than 0.5, which is a sign of the single photon nature of the photons of the stream. But this value was quite high, especially in comparison to the free space experiment, where it goes essentially to 0. But it's easy to understand where does this background come from. So this is simply the fluorescence from the fiber, which we cannot get rid of when we perform a CW experiment. So to sum up the performance of the molecule we have seen, we collected up to 50 kilocounts per second. The G2 of 0 goes lower than 0.5, and the emission is quite narrowband, so it's 28.5 megahertz, which is only 3 times larger than the line width of the D2 line of sodium. And this was already good enough to publish it and to say, hey, we have a very simple single photon source, which is narrowband at the same time. But there is still a huge room for improvement, because first we should perform resonant detection to detect not redshifted photons, but resonant to the 0 photon line. We should get rid of Raman scattering the fiber. We should try to couple to a single mode fiber and somehow increase collection efficiency. So let's briefly have a look at how can we achieve this. So the resonant detection, it's actually already an established technology, and I'm working on getting to there. So we can either perform cross polarization or 0-1 excitation, when we excite the molecule with 581 nanometer laser and observe the resonant photons which are decayed from the first vibronic state to the 0th to the excited state of the molecule. And another in order to get rid of the Raman fluorescence in the fiber, we can use so-called time filtering, which we discovered that it's possible. If the laser light, if we shine not a CW laser, but we shine pulses of laser light into the fiber, and if the pulse length is shorter than the time the pulse is propagating through the fiber, we can actually, carefully looking at when we detect photons at our APDs, we can see and separate the fiber fluorescence from the molecule fluorescence. And when we did the experiment, we've seen that one can see the large Raman, the fluorescence inside the fiber, and then a peak at the very end where the molecules are. But another more probably crucial question is how to improve the coupling into the fiber and how to couple to a single mode fiber. So these two questions actually can be answered at the same time. with the help of Simon Thiele from the Institute für Technische Optik and the group of Harald Giessen, we are trying to print now a 3D printed lenses on a fiber tip, which would in principle enable us to collect up to 60% or higher into the single mode fiber. So the design looks like is presented on the slide. The light is propagating from the single mode fiber, and then at the very tip, the molecules are located in the hole on the tip of the fiber, because I remind you that our molecules are in the liquid at room temperature, so we can soak it in. And in principle, when we coat it in metal, so theoretically, if we use not a single mode fiber but a multi-mode fiber, we can collect everything. But taking into account the dipolar emission of a molecule, we would still collect a lot, but it's not 100%. And such a lens was printed by Xenia. However, this one fell off, and this is the experiment I'm going to repeat during the next several weeks. But in order to actually get some results, I asked them to print a simpler design with a simple back reflector at the tip of the fiber. So the light is coming out from the fiber, and it's focused with the metal coated parabolic mirror, and then with the same route the light is collected back. So this lens is much smaller. That's why it would not fall off in the cryostat that easily. And I could see something which was very surprising for me, that with this simple design, I could see some photons into the single mode fiber. So of course, this is not the final result, but this is very inspiring that it's at least possible to see anything. So now I'm at the end of my talk, and I wanted to say that why what we are doing is important, because it's nearly ideal emitter. It enables atom-photon interfaces. It could, in principle, enable near-unity collection efficiency. And it also enables alignment-free collection of single photons. But there are a few challenges left, which are to be addressed during the next month, hopefully. So it's resonant detection, efficient coupling to a single mode fiber, and pure single photon emission. And maybe it will be possible to get it to a large scale quantum technologies by coupling a single molecule to a waveguide, to an optical fiber. So this is the team I'm working in. And it's amusing that 4 of the people on the picture are actually from the GAP, from MIPT, which I find amusing. Thank you. I'm open to questions and comments.
Thank you very much, Vladislav. It was a really nice talk. Now we have a little bit 1 minute for questions.
Nice question. Just as an outsider, so how does this technique compare with other state-of-the-art methods of generating single photons in the same frequency range?
In the same frequency range. So to be honest, I don't know other sources in this frequency range. Or you mean optical range?
Right, precisely.
Okay, in the optics, as I showed you, it is the best single photon source. So the thing is that it it shows the best remote Hongo-Mantel interference. So the photons are really indistinguishable, and the molecules can be really themselves are indistinguishable, such that the photons they're generating are very, very similar. And however, the only disadvantage of these molecules, the possible disadvantage, is their narrow bandness, which is at the same advantage because they generate less photons. So maybe, I don't know if you're familiar with, there are huge advances in the generation of single photons with quantum dots. For example, there is a group of Pascal Silena from France, and they have a lot of papers in Nature Photonics, regarding the nearly ideal single photon source. And they indeed generate a lot of single photons. Their Hongo-Mantel is very remarkable. However, they interfere the photons from the same source with itself. So there is a very big disadvantage other solid state emitters have. It's spectral diffusion. And due to the environment, their frequency jitters. And that's why the photons generated by them, they don't interfere that well as photons from molecules.
Okay, maybe quick next question. So you had this, at the end you mentioned the smart trick of chopping your pulse and using the timing as it goes back and forth to separate the signal from the molecule from the background. How does it improve your G2, this correlator, which shows that?
This is a very, very good question, Boris. Thank you for the question. So the problem I am having with this technique now, I did not repeat this experiment with this idea. So this is a very good question, because the fiber we are using is not single mode. So there's a lot of a lot of light propagating in the cladding of the fiber, generating this fluorescence. That's why it covers it, and it has some finite lifetime. So it covers a little bit the emission of the molecule. So this trick did not really improve the G2 function. But when we use resonant detection, if we would shine resonant light and detect at the same frequency, which is possible with smart trick with polarization, then we would get rid of Raman, because Raman is red shifted or blue shifted. So this is the approach of getting rid of this fluorescence from the fiber.
What are the temperature limitations for all these manipulations?
So yes, the molecules we are using are Fourier limited, so they are generating the best photons at 1 Kelvin. So this is really low, but the molecules we are trying nowadays, DBT in anthracene, they are claimed to have to perform as a Fourier limited source at 4 Kelvin, which is the temperature. It's perfectly fine to have 4 Kelvin Fourier limited single photon source, because we could use just a dual with helium and plug in a tube with a fiber, which I showed you before, and this would be already a super convenient single photon source.
Okay. Thank you very much. Thank you.
Thank
very
you,
nice, very nice tricks that you use. I was really impressed.
Yeah, thank you very much. Again, Vladislav, I believe it's time to move forward to the next speaker.
Yeah, thank you, Misha.
Just a second. And also Vladislav mentioned quantum dots. So speaking of quantum dots, I'm happy to present the next speaker, Fedor Meshchaninov from Moscow Institute of Physics and Technology and Joint Stock Company Molecular Electronics Research Institute. And together with Professor Leonid Fedorchkin, he worked on some very interesting problems using quantum walks. And today he will present the implementation of a quantum dot register with the usage of quantum walks. So it sounds very exciting. And I give the word to Fedor.
Thank you very much for such a kind introduction. Unfortunately, my camera is broken for today, so you will not see me, but you can see the presentation itself.
No problem.
Okay. Do you see the slides?
Yes.
When I switch them, is it okay?
Yeah, it works.
Okay. So, as Mikhail said, this work was made by me and my colleagues from the Institute on Physics and Technology of Russian Academy of Sciences. The work concerned the implementation of 2 qubits register with the usage of quantum walks of electrons over graphs of semiconductor quantum dots, with every dot being connected to quantum point contact. So let's go through the plan. First, we will talk about the motivation. Then there will be a brief introduction to quantum walks. The third point concerns continuous quantum walks. Then we will describe the systems we analyzed and make some denotations. And finally, we will proceed to 1 qubit gates and 2 qubit gates. So our motivation consists of 2 points. First is that the technologies for the production of quantum dots are currently widely used in many countries of the world, and as evidenced by various articles on this topic. In particular, we are interested in semiconductor quantum dots formed using electrodes. And second, what about quantum walks? They are promising tools used in the analysis of the behavior of quantum systems. In particular, they are actively used to speed up Monte Carlo methods in search algorithms, in quantum artificial intelligence modeling and image encryptions. So to introduce quantum walks, I propose to refer to the following classical example. A drunken sailor walks along a straight line, starts from the point with coordinate n equals 0 and takes steps forward and backward with probability 0.5. The evolution of the probability distribution along a straight line in this case is the simplest example of discrete quantum walks. It is known that this particular process is a discrete Markov chain. The set of possible positions of the sailor together with the lines connecting them represent a graph where the nodes are the points where the sailor can be, and the edges are the lines connecting them. In this case, the probability distribution evolves according to the equation pi of t plus 1 equals the sum over g of mig pg of t, where matrix M should satisfy the following conditions. Mig, all the elements of this matrix are non-negative, and sums along every column equals 0. If the sailor were a quantum particle, then it would be possible to make a replacement in the equations. The probability of finding a sailor at specific points would be replaced by the projection of his current state on states corresponding to the presence of the sailor at the points, and the stochastic matrix to the matrix of the state operator U. To demonstrate the difference between classical and quantum walks, we introduce an auxiliary space called the state space of a coin, and assumes that a sailor performs a quantum coin toss before taking a step. Then the state space of the system will become the tensor product of the state spaces of the coin and the positions of the sailor. And the operator U will take the form U equals S point CT, tensor product of CT and Y, where S is a shift operator, CT is a coin toss operator, and I is identity. Let's replace CT with the Hadamard operator. and define S such that when the coin is in the zero state, sailor shift to the right and otherwise to the left. Then, if both types of walk start from the origin and the initial state of the coin in quantum case is equal to 0 minus I1 over the square root of 2, in 100 steps, we will get that the sailor is most probably at the origin in classical case, and the maximum of probability distribution go away from the origin in quantum one with the speed about the square root of number of steps taken. There are also so-called continuous quantum walks, and the state evolution during continuous quantum walks is determined by the Schrödinger equation projected onto the graph node states. We have now considered examples of quantum walks in isolated systems, but there are also publications on quantum walks in the presence of noise. In our work, the role of graph nodes will be played by semiconductor quantum dots, and as a noise source, we will take quantum point contacts connected to each quantum dot. We will consider a set of diamond-shaped graphs of 4 quantum dots where all points of the graph can be connected in pairs by edges, except for the 2 farthest ones from each other. In this case, one spinless electron walks over each graph, and each node corresponds to one logical state of the register. Let us write the Hamiltonian of such a system in the tunneling representation, and in this case, the amplitudes of tunneling between the points will be assumed to be 1 if an edge is present, or 0 otherwise. Thus, the transition from one graph to another will occur by turning on and off tunneling. In this case, the system evolves according to the equation shown on the slide, where ρ is the graph density matrix, H is the Hamiltonian, and gamma is the noise parameter determined by the voltage drop across the point contacts. Here we note that we work in units where Planck's constant equals 1, and to obtain the required amplitudes in the Hamiltonian, we can renormalize the time. It is assumed that the quantum point contacts are approximately the same, and that the change in the tunneling amplitude from one reservoir to another with the appearance and disappearance of an electron in the corresponding quantum dot is many times smaller than the tunneling amplitudes themselves. Also, the temperature of the point contacts are kept at 0, and tunneling between the point contact and the quantum dot is prohibited. So before proceeding to the consideration of 1-qubit gates, we will accept the following notations. Let the graph contain only edges 0, 0, 1, 0 and 0, 1, 1, 1. Then the corresponding Hamiltonian can be denoted by listing all the included edges in subscript, but this notation is rather huge. It is proposed to pass from the binary system to the decimal system in the notation of the Hamiltonians and to denote the included edges with 2-digit numbers. Then the designation will be significantly reduced to H02,13. We will denote the corresponding evolution operators by U with the same indices. So now let's move on to implementing 1-qubit gates. 3 gates have been implemented: X, Y, and Z. Let's consider a gate X. To execute the X operator on the first qubit, it is necessary to leave only the edges between the nodes 0, 0 and 1, 0 and 0, 1, 1, 1. Then the Hamiltonian will be written as it is done on the slide, and the evolution for a given Hamiltonian during the time t equal p/2 is equivalent to the execution of x over the first qubit with multiplication by the common phase factor minus I. The action of the operator x on the second qubit is obtained by turning off the included edges and turning on the missing ones. Again, we get that the time t equal p/2, that after time t equal p/2, the NOT gate will be executed, but now on the second qubit and with the same phase factor. Performing gate Z for both qubits requires only one edge to be included in each case. If it is necessary to implement a gate Z on the first qubit, then only the H1011 is left. And for the second qubit, 0111. In both cases, the evolution time is t equal p, while operations Z are performed without any additional phase factors. Gates Y are obtained only by sequential application of gates Z and X. That is, the Hamiltonians already considered above with the evolution times indicated above are taken. In this case, operators Y are also obtained without additional factors. Now let's move on to qubit gates. Two of them were implemented C0 times CZ and controlled phase shift on pi. To make the first qubit, the Hamiltonians H12, 12,13 and H13 are required. Under the first Hamiltonian, the system must evolve during time t equal pi over the square root of 2, and as a result of which we obtain the logical block indicated on the slide in the first rectangle. Using the second Hamiltonian, we implement the operator Z acting on the second qubit. Gate CP of pi required the use of two Hamiltonians from the previous slides plus Hamiltonian H23. First, the evolution in the graph corresponding to the Hamiltonian H23 longs for the time t equal 3 pi over 2, and then the C0 times CZ gate is applied. We also simulated two qubit gates using the model potential. As an example of such a potential for a graph with one edge connecting points 0, 1 and 1, 0 is shown on the slide. For convenience, harmonic potentials were taken as the potential of quantum dots, and the barriers were approximated by Gaussians. In Hamiltonian itself, the Hamiltonian itself is written in harmonic potential units. Here in formula, Vi denotes the potentials of quantum dots. V barrier G is the potential of the Gth barrier. A is the quantum dot size. Ag is the Gth barrier height, and tuple X barrier G, and Y barrier G is the center for the Gth barrier. In our problem, A equals 1.5 and Ag is either 0 or 7. The accuracy of the gates at various values of the noise level was determined using the decoherence measure, the formula for which is written on the screen. Rho 0 here is the initial state, and lambda are the eigenvalues of the matrix rho ideal minus rho obtained. The reason why we chose this measure is that it is additive and gives the estimate of evolution deviation in the worst case of all possible ones. So also we used the theorem that one can search only through pure initial states of the system. As one can see, the simulation gives us some errors in evolution, even if point contacts are switched off. The decoherence measure is about 0.2 if gamma is 0. But all curves demonstrate the same behavior at large values of noise parameter and go to value about 0.75. The accuracy can be improved by changing the forms of barrier potentials. So let us summarize all that was said. The possibility of implementation of 2-qubit register on graph of 4 quantum dots is considered. Hamiltonians for 2-qubit and 1-qubit gates are found. 2-qubit gates are simulated with the usage of model potentials. The influence of noise on 2-qubit gates accuracy is calculated. The accuracy of the gate implementation can be improved by using other types of barrier potentials. So thank you for your attention. Now I'm open for your questions.
Yeah. Thank you very much, Fedor, for your interesting talk.
I'm sorry.
Yeah, if you have any questions, please, we have some time.
May I ask a basic question about the general motivation? What kind of natural process or what kind of technological application do people have in mind when they investigate this random quantum walks?
What kind of natural process? So we can say photosynthesis, electrons. The evolution of electrons can be explained like random, like quantum walks on a certain graph in a plant, for instance.
So coherent quantum transport in photosynthesis, right?
Yes, I think so.
Okay.
Thank you for your questions. So I think we can go to the next presentation.
Okay, if no other question, yeah, then thank you again, Fedor.
Thank you.
It's really interesting. Okay, the next. Yeah, so the next two talks are parts of the big project on machine learning applied to quantum information processing. And the first speaker, Alena Mastiukova from Russian Quantum Center, which you probably remember from the first day of the conference. And we had a pleasure to hear talk from Alexey Fedorov and Evgeny Kiktenko from Quantum Center. And today we have a pleasure to hear a talk on machine learning for the classification of entanglement from Alena. So please, you can start your presentation.
Hi, I am Alena and I am a junior research fellow at the Russian Quantum Center, and also I am master student at MIPT. Today I want to tell you about the problem of machine learning which we are dealing with our research group. I want to know right away that it will consist of two parts, the second of which will be told by my colleague Maksim Gavreev. The task that we will tell you about today is machine learning for classification of entanglement. First, I'll do a brief introduction and tell you a little why it is interesting and relevant. Nowadays, a growing interest in exploring machine learning methods in the context of quantum physics results in the development of various techniques for learning phases of matter and learning phases transition, and also efficient representation of many-body quantum states and automatization of experiment. So among various fundamental aspects and applications of quantum phenomena, quantum entanglement plays a critical role. That is why the detecting entanglement problem gains significant attention and it is subject of research work in the context of machine learning. For small dimensions of the system, there is a criterion for determining whether the state is entangled or not. It is positive partial transpose criterion or PPT criterion or Peres-Hordetsky criterion. But already for large dimensions of the system there is no such criterion. In this case, it is necessary to construct a certain classifier of entanglement of quantum system. Machine learning techniques seems to be a profound solution, since the problem of determining entanglement for a given quantum state is in general an NP-hard problem. A promising way to study quantum system with machine learning is the learning by confusion scheme, which has been originally used for detecting the topological phase transition in the Kitaev channel in this work in Nature Physics. In this work, we present a method for the separability-entanglement classification problem, which based on the machine learning with confusion method that uses SIG-POVM's probability representations. So first, let us describe the confusion scheme itself. Confusion scheme typically used to find a transition point in some parameterized dataset. The scheme works in the following manner. We consider a parameter pi on the segment from A to B, for which we know that the system in phase 0 at point pi is equal to A, and it is in phase 1 at point pi is equal to B. So we assume that there exists an unknown critical point PC on the segment from A to B. And we then propose some critical point P0 and train the neural network by labeling all data with parameters smaller than pi0 with label 0 and the others with label 1. For this configuration, we evaluate the performance function pi large of the network on the entire dataset. By maximizing the performance, we obtain the true value of critical point PC. It is peculiar that the performance function pi large has a universal W shape with the middle peak at the correct critical point PC. And in this work, we get a universal W shapes for several cases. In one of them, we focus on entanglement classifier for 2-qubit entanglement states, also known as Bell states, with the use of a depolarization channel to construct a dataset. First, we will describe how exactly we build dataset for training neural network in this case of 2-qubit system. In the Hilbert space HA tensor multiplied by HB, we consider a Bell entangled quantum states in the following form. The density matrix of the maximally entangled states is as follows, and for this density matrix we generate a random depolarization parameter alpha in order to extend our dataset and act on the state by depolarization channel given by this equation. Next, we use local unitary rotations operator. We generate these random rotation operators using the IBM cascade function. These operators U are distributed according to the Haar measure. At this stage, we prepare some first data. It consists of the following set of U rho alpha data, U dagger and alpha. Here, alpha is used as label, and U rho U dagger is raw random density matrix. The next step to prepare dataset is to use SIG-POVM measurements. The final dataset for the neural network is formed as a set of a result of SIG-POVM's measurements and labels. We train neural network using the set SIG-POVM's measurement probabilities MIG, and we consider the SIG-POV measurements of an individual qubit a set of 4 local projectors. Thus, at the stage we have finished building the dataset, it will be specified by such set MIG and function f alpha, where this function has the following form: is equal to 0 at alpha at this alpha and is equal to 1 at this alpha. Next, we will describe the structure of neural network. The neural network that we use in this work has a feed-forward neural network's configuration. Its total encoding structure is 16 neurons in the input layer and 32 neurons at the hidden layer and only 2 neurons in the output layer of a 2-qubit case. We use L2 regularization and L1 regularization function in order to avoid the overfitting of neural network. The cost function is as follows. Here, the first term is the loss function, the second term is L1 regularization term, and the third term is L2 regularization term. And also we use Adam optimizer for optimization of our process of neural network. To check the correctness of the neural network work, we can use several characteristics for a 2-qubit case. We use concurrence, which is a function that quantifies the amount of entanglement present in quantum states, where lambda 1 or lambda 4 are eigenvalues in decreasing order of the Hermitian matrix R. So such a characteristic as concurrence gives us the most efficient approach to determining and quantifying the entanglement of a quantum state. This feature is useful for determining the entanglement of a mixed states. If the concurrence is 0, the quantum state is separable, otherwise it is entangled. Another characteristic of entanglement is negativity. We also use it for a measure of quantum entanglement. The negativity of a subsystem A can be represented as this equation, where lambda I are all of eigenvalues of the partial transpose of ρ with respect to the subsystem A. In some cases, it is more convenient to use negativity as a characteristic of entanglement. Finally, we realize the learning by confusion scheme, and we present the result of training of 2-qubit quantum system in this figure. On it, we see typical W-shaped. The transition are expected at the point where alpha 0.3, and as we see, the maximum of the W shape is at this point. We also see a change in the two characteristics at this point, concurrence and negativity. Also, we propose a different approach to constructing W shapes. We used XGBoost to speed up our learning, and indeed the speeding of learning in this case increases. The so-called gradient boosting XGBoost is a machine learning technique for classification problems. This technique builds a prediction model in the form of an ensemble of weak predictive models, usually decision trees. And this technique already includes regularization, so it doesn't require separate inclusions in the cost function. The results for such training of 2-qubit case are also present in this figure, with orange. And next, we use the same procedure for constructing W shapes for the case of 2-qubit quantum states, and we show that the accuracy does not decreases with increasing dimensions and remains at fairly high level. And the results for such training are present in this figure. So let us move on the conclusion of this work. The neural network was trained to classify entangled states by its measurement probabilities. This approach can be easily generalized to classify many qubit states. Learning by confusion method was tested to find the phase information transition. It can be used to find the entanglement destruction threshold of unknown channels. And now we continue to work on improving the learning by confusion method and are preparing a publication on this topic. Here I will say that my colleague in his next talk will tell how we continued this work and what result we got when constructing a classifier of any input states using a special channel. Also, I note that such a case with depolarization channel is interesting because many qubit GHD states are something that is interesting to do an experiment, for example. Thank you for your attention and keep in touch. You can ask your question about the work after the next talk, where my colleague, as I said, will tell the second part. Thank you again.
Yeah, thank you, Alena. So, okay, probably it is really better that Maksim Gavreev will continue this talk. And after that, we can ask our questions. So, Maksim, are you ready?
Yeah.
Okay, great. So Maksim Gavreev is also from Russian Quantum Center. Okay, and without further introduction, you can start your talk.
Do you see my share? Hello?
Yeah, now we can see. Now we can see the presentation. Yeah.
Okay. So I would. I'm glad to dive you into some details about the topic. So it is very interesting that actually, as my colleague already said, we find that neural networks actually can learn the entanglement criterion, which is nowadays is developed only for special cases. But firstly, a brief introduction. So if we consider a bipartite system, A and B, which lives in a Hilbert space HA times HB, so state rho AB is called separable if it can be written as some convex combination of two density matrices living in HA and HB separately. So the lambda i's here is a probability distribution. So if any state can be written in such form, this state is called separable. Otherwise, it is called entangled. So what the entanglement measures we have here, as my colleague already said, we have concurrence and negativity as measures of entanglement, but otherwise there is no necessary and sufficient criterion for large dimensions when the dimension of A space times dimension of B space is larger than 6. We have only sufficient criterion like negativity, but it is not necessary. So if the state has negativity in any dimension, you can say that it is entangled. But if it's not, if the negativity of some state is equal to 0, you cannot actually say anything about the entanglement of this state. So in addition, the entanglement, such entanglement detection problem is proved to be hard, but no, it is obvious, as you can see. So if we see about If we look at this formula, you can notice that actually the separable state space is convex with the pure separable states on the boundary. And as my colleague already shown, we actually can find a transition point from the between a separable state subspace and entangled state subspace. So such point is analytically known for equal dimensions of subsystems for a depolarizing channel. So if we have some method which can find this transition point, it is easy for us to check that it is correct. But otherwise, we already can can solve the problem of finding such a transition point between some subspaces, but it can be used in entanglement detection problem only if the state which we call input is already in the prepared data set. The problem for us here is to construct such a data set which is determined by the input state. And we propose here a state generation procedure. So let us consider some input state rho in, which we want to say about it, is it entangled or not. We can consider its spectral decomposition, and then we can easily say that it is some thermal state with T equals unity of some specific Hamiltonian. And then we can revert specific Hamiltonian in such form where lambda is the generalized Gell-Mann matrices. So we can make it for any dimension. And so such Hamiltonian consists of two parts, which is local part and non-local part. So we should note here that only non-local part can produce the entanglement. Between the local is just a interaction with the local field of one of the subsystems. And the non-local is the interaction between subsystems which can produce the entanglement. So we have to construct the map from the entangled state space to separable state space. To do this, we introduce the dependence of the general Hamiltonian on the such parameter gamma between 0 and 1, such that the 2 gamma on the local part of Hamiltonian on the some multiplicator on the non-local part. So you can see that for gamma equals 0, there is only non-local part of Hamiltonian, and for gamma equals 1, it is only local part. And then we can construct the state parameterization such that where temperature is something like is given by this formula. And then by construction, we have rho from at 0 point is will be a maximally entangled state. Actually, if non-local part, as soon as non-local part of Hamiltonian has its ground state as a maximally entangled state. At point 1/2, our state is actually input state, and for gamma equals unity, there is our state is maximally mixed state. So actually, the procedure looks like the following. So we generate the states rho gamma from such a construction with random gamma. Then we rotate each state with random local unitary operators. It is for unitary operators, it is necessary to be local because the entanglement properties are invariant only under local operations. Then we measure two subsystems by some set of sig-poems, and then prepare such data set like the measurement results, measurement probabilities, and parameters gamma. Then using a confusion scheme, we evaluate the performance of the neural net according to each parameter gamma, and then we just find maximal accuracy, or we find the parameter for each the neural net has the maximal accuracy, and if this gamma transition is less than 1/2, the state is separable. Otherwise, it is entangled. So here the results is presented for the 2-qubit case on the left. Here we test the example of entangled state and of separable state, and there is a result for 2-qubit case for entangled and separable states too. So as we can see, there is a very visible, pretty visible double V shape showing the transition point here, and by the position of the maximum of this graph, we can say whether input state is separable or not. So there is a quite interesting that for confusion scheme, we not the overfitting of our model is not necessarily bad, because it can increase the visibility of double V shape, and allowing us to determine the right transition point with higher precision. So there are a list of some parameters used for qubit and qubit cases. So what we can say in general, that we have constructed a separability-entanglement classifier based on the confusion scheme, and we demonstrate the ability of neural networks to learn the difference between entangled and separable states only by the measurement results, which is pretty interesting. And we hope that the results of this work can help to formulate analytical general criterion of entanglement. So that's all for now. Thank you for your attention. If you have questions, you can ask.
Thank you very much, Maksim, for a very nice talk. Yes, so we're a little bit ahead of the schedule, but I think it's okay. So we have time for questions.
If no one asks, may I start?
Yeah, sure.
Okay. So I have two questions. One perhaps about the broader motivation and another about technicalities. So as far as I understood from these two talks, part of your motivation is to use entanglement as a diagnostic tool for phase transitions. Is that correct?
It is. So I would like to say that we use the methods, the machine learning methods, which was previously used for unveiling phase transitions to actually detect the transition between entanglement and entangled and separable states.
Right, but so what I wanted to ask is this. So I suppose, even though these criteria of entanglement are not clear yet for many particle systems, I think it's a reasonable expectation, like the one shown on one of your slides, that you have like a sphere of separable states, and then after that, yes, like this, and then entangled states come. Tell me if I'm wrong, but I think in a typical many particle system, this border doesn't have much to do with phase transitions. That it probably exists somewhere, but it is hard to identify. But I guess there are many questions, many cases when it is just some point, for example, as a function of temperature, which doesn't indicate phase transition. What can you tell me about?
So actually, you can so previously such methods was used to unveil phase transitions to find the transition temperatures and so on. From the example with depolarizing channel, we have seen that the neural network fed by the measurement outcome can actually detect something that is invariant under unitary rotations. And then we're trying actually to build a entanglement classifier, but yes, the phase transitions and some entanglement separability transitions are connected in various models. Maybe in some cases the points are the same. That was your question.
I mean, yes. I mean, the question is that there may be some probably exceptional cases where entanglement transition coincides with the phase transition. But I would say, though, I would expect those cases to be rather exceptional. And the typical case, I don't know if you have heard, some years ago there was an activity which was called sudden death of entanglement. It was looked as a function of time or as a function of temperature, and then, say, for example, concurrence was just suddenly disappearing from the system without any relation to whatever other measures of phase transition, like specific heat or something. Right. So
I didn't know about that. I think it is pretty interesting. And maybe we can do something with that cases. Maybe it will be interesting. But yes, it is from my experience with from playing with this thing, in various cases, the entanglement transition and phase transition are coincide, but it is not necessary, as I think.
Okay.
So some.
Okay. Now, I might ask you just sort of technical question. So as you were discussing, the basically classification of entanglement in many particle systems is basically a long-standing challenge, and you use this separability criterion, which is difficult to check, right? And so you use neural networks for that. But say, suppose I do have a many particle system, not qubit, qubit, but really something that has more components, more qubits, for example. Then what should I expect from this neural network kind of machine learning exercise? So suppose your scheme produces for me a way how to represent a given wave function or given density matrix as a separable state. Then, of course, it would guarantee that the state is separable. But if, on the other hand, your scheme does not identify a separable state, how confident are you going to be that the actual state is separable or not? What is your understanding?
The understanding is if actually this scheme works perfectly when you have like a bunch of samples of states or something, and the neural network actually tries to find the difference between like two parts of this large collection of data. So it tries to find some logical difference between them. Actually, it for the neural network, the separable state and the entangled state are it doesn't seem the difference between 0 and 1 actually. I can just so it doesn't know anything about something like separability or not separability. So it just tries to split a data set on two parts, on some with some logic.
Well, I suppose my question still was like that. I mean, how would you test, I mean, in general, your scheme for many particle systems where you actually don't know whether the state is separable or not? So suppose your neural network predicts something. So as I said, if the state is separable, okay, you can show each is separable. But if each is not, how would you test this method for larger quantum systems?
There is a problem with testing, actually. As my colleague already shown, the case with depolarizing channel, it actually has an analytical solution for arbitrary large dimensions, but when the dimension of part A is equal to dimension of part B. So actually they all have analytical like formula determining the position of such a transition. And there was a part of our work where we try we use actually depolarizing channel because it gives us analytical criterion, and we can check does the neural net works correctly or not. For very large dimension systems, it is a real problem with actually checking the answers, the predictions of neural network, because we actually have no criteria, and we can say only what the neural network can say.
Okay, yeah, thank you very much.
Yeah, so in that case, it would be unsupervised learning, right? Because your data will be not labeled.
It is like a combination of supervised and unsupervised. Actually, on each step, I made a super, but I made it for any possible labeling. So actually, I have no supervisor here. I trying to determine the labeling based on the performance of neural net, of her ability to learn some patterns in data.
Okay, yeah, thank you. That's interesting. And also, may I ask a quick question? So you said that you use density matrix as an input for your model. Is it right?
Actually, we preparing on this stage of dataset preparation, we actually measure the density matrix by SIG-POLY set. So we on the in the input of the neural network, we have a probability distribution actually.
Okay, yeah, that's great. I'm just curious about the scaling when we work with a large scale system, but yeah, I see. Okay, great.
So the scaling will be the same actually. So there is still a problem.
Yeah, now I see. Yeah, thank you. So now if we have any more questions, then we have some time to discuss it. Okay, if we don't, then I would like to thank Maksim and Alena again. It was really interesting topic. And so unfortunately, it was the last talk at our wonderful online conference. And once again, I want to thank you all, such nice talks, presentations, and questions. And I hope that we will see each other face-to-face soon, and our next meeting will be definitely offline. So for the conference proceedings publications, we have already sent you an email with all necessary information. And also some recordings, video recordings, have already appeared on YouTube, and we will publish the remaining recordings in the next few days. And for any questions about recordings or conference proceedings, please feel free to contact me via email. And to this end, we're finishing our conference, MIPT Quant 2020. It was a real pleasure. Thank you very much again. And I leave the final word to Professor Lesavik.
Thank you very much, Misha. Is all right? Do you hear me?
Yes, we can.
Okay, gentlemen, it is really nice to see you at least on the screen. It will be, of course, much better to see you in the real life, and indeed, we hope everybody that soon it happens. Thank you very much for participating. So it was new for us, although last semester, of course, we already teaching online and so on, but still for the conference, it's sort of new experience. We managed, and to a great extent, thanks to Misha Perestein, who organized it excellently, and other guys like Nikita Kirsanov and others. So thank you, and thank you for supporting that by your participation, and please, don't forget to contribute by your articles. Okay. All right, gentlemen. It's a pity to say goodbye, but it's time to do it. Thank you very much again.
Bye. Thank you.
Thank you. Bye-bye.
Thank you.
Goodbye.